Si, comme ça, quoi.
All right. So today it's my great pleasure to introduce you Benoit Famaey from the Observatoire Astronomique de Strasbourg. We're visiting us today and tomorrow, thanks to the X-Gal tuning funds. So Benoit did his thesis in 2004, in 2004, in University of Brussels and in Gand. After that, he moved in Oxford, then Brussels, then Bonn. In 2019, he started a senior position in Strasbourg. He had a really great PhD student for 3 years. And since 2019, he is a director de recherche, so a current professor. He is one of the co-PI of Reef Galactic Ecology Low Resolution Disk Survey, and he's doing many things, either by studying the Milky Way, but also his other big part of work is about alternative work on called dark matter theory. So that will be the subject of the talk today. I will try to not break everything. So, the floor is yours.
So, thank you very much for the invitation to give this talk. So yes, as Guillaume was saying, I mean, a lot of my research interest is about modeling the Milky Way in general, using Gaia data, maybe one day WEAVE data. And another part of my research, I mean, these two things are obviously related. Let's say that the focal point of my research, including the one on the Milky Way, is to learn something, or maybe even more than something, about the nature of dark matter. I think it's the case for many people who are working in the domain of galactic dynamics. So now in this talk, I'm going to present you a very, I guess, subjective overview of the things that don't necessarily fully make sense yet in the LambdaCDM cosmological model, which might perhaps indicate that we could or should or might move away from it. At the same time, I'm going to show you that it's not easy to find alternatives. That usually when you introduce an alternative to solve one problem, you create other ones. And so obviously, if if we knew the solution, we would all adopt it, but we don't. So anyway, let me start by saying a few basic things that I think are not too controversial. They might be for some people, but I don't think it is really controversial. The fact that we need something like dark matter at cosmological scales. So here I like this short picture, which is basically showing us the history of the universe in one plot, where you have the log of the redshift here. We are here. CMB is emitted here, and this is the energy density in the different components of the universe. So you have the radiation in red, which is falling down faster than matter. And you've got the dark energy in blue, which is completely subdominant at the beginning, and which starts being dominant a little bit before our present day. So there is an arrow here where I say that we need more matter than is actually present in the baryons, and the best evidence for this, I think, comes from the CMB itself. So this is the angular matter power spectrum of the CMB that you all know. It's useful to remind in a few words why this implies that we need something like dark matter. The reason is that so you see each of these peaks correspond to compression rarefaction waves that are entering the horizon at earlier and earlier epoch when you go to smaller and smaller scales. And it turns out that if you would only have baryons in accordance with BBN, then the second peak here, which corresponds to a rarefaction peak, would correspond to a peak that has entered the horizon when the universe is still dominated by radiation. And in the radiation era, you have a phenomena which is called potential decay, which is related to the fact that the density of radiation is falling really fast, which means that in a rarefaction motion, basically the amplitude of the second peak should be much larger. Basically, the potential decay is boosting the rarefaction peaks, and so the presence of dark matter is absolutely necessary to damp the second peak. So this means you have to increase the amount of matter that you have in the universe, and it cannot be baryonic matter, because if you would just increase the amount of baryonic matter, let's forget about BBN, then you would also have another effect which is called baryon loading, which is basically boosting the compression peaks, and so the first peak would become gigantic. So if you want to keep this equilibrium between the first, second, and third peak, and so that the second is not much larger than the third, the only way is to damp the second, and the only way to damp the second is to increase the amount of matter, and it must be non-baryonic matter, because otherwise you have baryon loading and you don't match BBN either. I think a second line of argument that we need something like non-baryonic dark matter comes from the matter power spectrum. So you also all know about it. Is the Fourier transform of the two-tonic correlation function. It's the dimensionless power spectrum here, which is basically a measure. It's directly proportional to the variance of the contrast density as a function of scale. So here you have the radial wave number, which goes to large values, so correspond to small scales. So basically, it's a measure of clumpiness as a function of scale. And so the measured one is showing us that this dimensionless power spectrum is increasing when you go to small scales. And so that's the fact that the matter power spectrum, that its amplitude is larger than the one you would expect without dark matter, is the old indication that from the perturbation that you see in the CMB, 1 in 100,000, it's not enough to form enough power at the redshift corresponding to today. But that's not in principle. That's you could just boost gravity and that could work. But in addition to this, in principle, if you don't have dark matter, the translation of the CMB angular power spectrum in the matter power spectrum leaves an imprint, which is that you all know about too, which is called the baryonic acoustic oscillations. But the BAOs without dark matter, they would be much more pronounced. And it would be only this, right? That would be the seed of structure formation, and that would leave imprints resembling this in the matter power spectrum. Of course, with non-baryonic dark matter that is decoupled from the baryons prior to recombination, you already start creating the potential wells before the CMB is emitted, and then the baryons fall into the potential wells of dark matter. Then you still have BAOs in the matter power spectrum, but they are much less prominent than if there would be only baryons. Of course, the BAOs are still there, but you can use them as a rod to measure the expansion of the universe. So these two things together really mean that we need something like dark matter. I've put quotations here because, and the last thing is that we need something like dark matter, and we need it to be called in the sense that if it's close to relativistic at recombination, decoupling here, then you tend to damp the power spectrum at small scales. And so if you want to form structures all the way up to large K values here, you need your dark matter to be cold. And so that's it. It's called dark matter. You add the dark energy here. That will give you omega total equal 1 to explain the shape of the CMB plus the acceleration of the expansion of the universe. Everything is fine. Problem solved. So I put quotation marks because, of course, I mean, if you only look at what I just said now, Occam's razor is indeed telling you that we live in a lambda cold dark matter universe. But are the data really proving us that we live in a cold dark matter universe? And if I concentrate on the dark matter part, or cold dark matter part of LambdaCDM, are we sure that dark matter is really matter? And so if we just consider for the moment cosmology, I'm not talking yet about galaxies, you can consider a framework that has been introduced by Hu in 1998, which you could call generalized dark matter, right? So you can consider a very general fluid that has non-zero pressure and that has also anisotropic stress, right? So meaning that the pressure depends on the component of the tensor that you are looking at. So basically, you have an equation of state, which is the usual W, that is the pressure over density that is equal to -1 for dark energy. But here it's typically 0 for CDM. So you can have something like an equation of state that varies as a function of the scale factor. So this is just a parametrization, right, of something. And then you can have a sound speed that also depends on both the wave number, the scale, and the scale factor, or the redshift. You can also have a kind of viscosity in your fluid. So you parameterize your generalized dark matter fluid like this. And this kind of very generalized dark fluid can typically describe the evolution, for instance, of a k-essence scalar field. So it's a scalar field for which you will have a potential that will not depend, as usually, on the scalar field itself, but on the kinetic term of the scalar field. And this can give you this kind of gravitating fluid, which has this varying equation of state as a function of redshift, varying sound speed, varying viscosity, etc. And so I'm already telling you that this kind of fields is typically what you need in the most radical alternatives to LambdaCDM, which are relativistic one theories of modified gravity. They always induce, mostly, I mean, there are also other ways to do it, but the usual way to do it is to introduce a k-essence scalar field. And if you have a 0 point for the scalar field, which is not 0, for this potential of the scalar field, which is not 0, then the field that is going to modify gravity is also going to gravitate, but it's not going to gravitate like dark matter, but like something that has a variable W. And in fact, I mean, you probably have all seen, and you all know about the DESI data on BAOs that are not fully compatible with W equal -1 all the way through the redshift range for dark energy. But usually, when you do these fits, you always assume that the dark matter part is untouched, right? But if you also let the dark matter part free, here you have this plot by Illich et al. In 2021, which is based on the power spectrum plus lensing data plus BAOs, which is basically a constraint so they do the constraint on the sound speed, they do the constraint, they calculate the constraint on W, on the sound speed, on the viscosity. Here I'm just showing W, right? Because I think that's a good way to ask ourselves whether we agree on what matter is or what matter is not. But in principle, so there are indeed scale factors essentially close to the CMB where you need W to be really close to zero. So it means that the dark fluid, whatever it is, behaves like dark matter at the decoupling time or at recombination. But if you use all the constraints that you have on W as a function of the scale factor, you end up, I think this is the 2 sigma limit, or one, I think it's only 1 sigma, or maybe it's 2, I forgot. But anyway, you see that you have a lot of wiggle rooms for your dark matter in your cosmological expansion to be something else than cold dark matter. And so people have written this with the ZDR2 recently. So here it's not the scale factor, it's redshift. So now we are here. And you see that the best fit for the W of dark matter is basically negative at z equals 0, and also quite significantly. So here the one sigma error is already in agreement with 0, right? So 0 is fine. But here, I mean, close to 2 sigma, you start at redshift of 1.5. You start preferring a negative W for your dark matter component. And so I guess we can all agree that if the best fit would be a fluid that has a negative W at some redshift, this is not matter, right? I mean, so that's why I put quotation mark when I say we need something like dark matter in cosmology. True, but we don't need dark matter. I mean, no one would call this matter. It's not, and this cannot be due to particles, something that would behave like this. I'm not saying that things behave like this, but cosmological data are not preventing this from happening. So now let me move down to the scale of galaxies and give you the kind of subjective overview that I promised you about what I think are limitations, that maybe there is something going on at these scales. Yes. Something we see. Yeah, I mean, I forgot exactly how much if they fix the cosmological constant, whether the effect that you see here is that generate with the variation of W for dark energy, right, as a function of redshift, right? When you let both at the same time, maybe you can have something, a scalar field that is doing both dark matter and dark energy, and the combination. But here, I think you have the 1 sigma line, which is supposed to be the black thing here, and the 2 sigma, which is here, right? So basically at 1 sigma, it's kind of agreement. Whether they can have local situation here and there, might not be problematic for the point of view of statistics. Right? No, I don't think anyone is saying that there is a statistical evidence that W is varying with redshift. It's the other way around. He's saying it's not incompatible with not being matter. So when people tell you it's dark matter, we know it's matter. I'm just showing you that in principle it's completely compatible with it not being matter. But there is no statistical evidence that it's not matter. the evidence, if quote unquote evidence, it will rather come from, I mean, the way you interpret what is happening on galaxy scales. But it's just that there is some wiggle room for models where you are going to introduce some kind of modification of gravity with new fields, where your new fields are going to behave a little bit like dark matter, but not completely. And I'm just saying that cosmology is not preventing this. There are constraints. So yes, galaxies. Let me also be clear that we are deep, of course, in the nonlinear regime when we talk about galaxies. So the physics is more complicated than when you look at structure formation on large scales. So you have to rely on simulations. You have to rely on baryonic physics, which you have to model through subgrid recipes. So it's all very complicated. Simulations have made huge improvements at forming more and more realistic galaxies over the years. But some tensions do persist, and here I've chosen a few examples. So let me start by a tension which is not really a tension, but that was a big, well, it was quite popular, let's say 15 years ago, the too big to fail problem. So basically, what it tells you is that if you look at dark matter only simulations of the formation of dark matter halos that are supposed to host a galaxy like the Milky Way, you look at the satellites, the subhalo satellites of your main halo. You take all these subhalos, and as a function of the mass of your host halo, you plot the rotation curves, the circular velocity curves of these dark halos as a function of the mass of the host. So here you see you go from 2 times 10 to the 12 down to 1.3 times 10 to the 12, and basically and here you have the circular velocity curves at the half-light radius, the circular velocity estimated at the half-light radius for actual satellites of the Milky Way. And so basically the idea of the too big to fail problem is to say, where are these things? And so they are too big to fail. I mean, these are the densest subhalos that you expect around a galaxy like the Milky Way. So why did they not form stars? I would say that I mean, all these estimates for the mass of the Milky Way are a little bit on the high side to start with. Nowadays, I would say that there are not many estimations that go much above 10 to the 12 solar masses for the real mass of the halo of the Milky Way. And also, you can, I mean, these were for DMO simulations, and in principle, you can solve this with feedback by basically changing the profiles, rendering the dark matter halos of these densest dark matter halos of the Milky Way, rendering them less dense through feedback. Good. So I think this is a good example of a tension that people have been discussing for a while that is not really a tension anymore, but there is I think a related problem where some cores that you need to have in your satellites of the Milky Way, but also of Andromeda, are just too large for any CDM simulation to explain them. And this is what we call the feeble giants problem. So feeble giants in the sense that these are large galaxies for satellites, right? They are quite large, with typical core radii, half-light radii that can be as large as 1 or even more than 1 kiloparsec, and feeble in the sense that their velocity dispersion is really, really low. And so a prototypical example of this is Crater 2 around the Milky Way, but you also have Antlia. There are a few, I put a few here, Antlia 2, Andromeda 25, Andromeda 21. These are all feeble giants. So let's take Crater 2. It has a half-light radius of 1 kiloparsec and a velocity dispersion of only 2 kilometers per second. And so this paper by Borokov-Tskaya et al. In 2022, these are a few authors, including Raphael Errani, who was a postdoc in Strasbourg at the time when this was published. They really tried hard, right, by showing you that if you start from different initial velocity dispersions in a dark matter halo that has a circular velocity, an initial circular velocity that resembles this. So this, I think, yes, this yellow line here is supposed to represent the R max V max relation for CDM halos that are not in a tidal field, right? But we know, of course, that Crater 2 is around the Milky Way. And so here you start with different possible stellar velocity dispersions. So this will be the velocity dispersion for these points. And this will be the half-light radius on this axis, and so you let them evolve inside the dark matter halo that could bring you more or less to the right Rmax Vmax, and all of these initial velocity dispersion for your stellar component, they're all going to converge to velocity dispersions that are close to the observed one, close to 2 kilometers per second, always at much smaller half-light radius than what is observed for Crater 2. So the conclusion here was really that if you don't start for some reason with a halo that is more coarse than in LambdaCDM, then it's impossible to reproduce Crater 2. And there are not many other ways to start for a galaxy like this, to start with a core than by changing the nature of dark matter. Feedback is not supposed to solve your problem here. So I think this is a real problem, and the fact that Crater 2 is not alone, but that there are other galaxies sharing the same problem, is really indicating that there is something that is not right. Or maybe we have bad data on all these galaxies, or they are out of equilibrium, or whatever, right? But this is something that we should continue to investigate. So now on the simulation side, so here I'm not claiming that this is as serious a problem as the one I showed. An interesting thing, maybe that I forgot to say, is that there were also a few papers in simulations claiming to reproduce these things, and the thing that this group showed is that this was a resolution effect. So that's all the papers claiming that they could explain this were relatively low resolution simulations, but that when you increase the resolution, then you converge to something that cannot explain the observations, right? So you can with bad resolution, but with good resolution, you cannot. So the hot orbits problem, or the bulge, stellar halo problem, or spheroidal component problem of simulations in general. So this was put forward, for instance, by Jim Peebles in 2020. So basically, if you take not the bulge to total ratio in simulations, but the bulge plus stellar halo relative to total stellar mass in simulated spiral galaxies from simulations that are otherwise performing quite well, like Fire 2 or Riga. Basically, you have nothing that can go below 25%. But if you look at the B over T, and so B here is, so it's the bulge, and honestly, you can include the stellar halo in the B over T ratio, because the stellar halo is so ridiculously small that it doesn't change anything. Well, basically, you peak below 20%, right? So these galaxies that are usually claimed for many other properties to reproduce observed galaxies quite well, when you look at the bulge plus stellar halos relative to total in the simulation and in observations of spiral galaxies close to the Milky Way, we are really far off, right? And so, again, this could be due to baryonic physics not being well understood. In general, these further components, they really come from the history of formation of the spiral galaxies in these simulations. It's not so easy to get this pure disk with a very low mass bulges and low mass stellar halos in galaxies without changing the actual cosmology. So in this article in 2020, Peebles was arguing that maybe this was one of the, from his point of view, an argument against LambdaCDM cosmology, and showing that maybe galaxies are not born in the way we think they are born in that context. An even more, let's say, maybe easy to solve problem, but that is interesting nevertheless, is that when you look at the details of the galaxies that are formed in simulations, if you look at the statistics of the most obvious non-axisymmetric signature of galactic disk, which are bars, the statistics are, you can always find a galaxy where the bar looks nice. If you look at the statistics, it's a catastrophe. So around stellar masses of 10 to the 9, 10 to the 10 solar masses, in the observation, 70% of these galaxies are barred. In simulations in general, the statistic locally is bad, and if you look at the statistic with redshift, it's even worse. So usually the trends are reversed. It doesn't look at all like what we observe. And on top of this, the observed bars are almost always relatively fast. with a co-rotation radius which is basically close to the radius of the bar itself, while in simulations the bars are way too small compared to their co-rotation. Let's put it that way. I think if you look at simulations like Illustris, the typical pattern speeds, and so the location of the co-rotation is good statistically speaking, but the actual size of the bar is actually way too small. So that translates into these slow bars where the R parameters, the ratio between RCR and R bar, is way too large in the simulation. So that's very generally the case in simulation. Yes, this one I'm not going to spend too much time on it, but I just think that the jury is still out on this one. I think there are no real alternatives that can explain things better than LambdaCDM, where it could just be a statistical anomaly. I really think that anomaly, I don't know what you call an anomaly. Well, at how many sigmas do you start calling things an anomaly? But basically, it's the plane of satellite problem that has been discussed for, I think, for more than 20 years, a bit more than 20 years. And so basically, if you look at the distribution of satellites around the Milky Way disk, which is here, obviously, it looks like a polar ring and not like the isotropic distribution that you expect. This can happen quite often because, I mean, the satellites are accreted on filaments, etc. The thing that happens less often is that if you look at the actual velocities of these galaxies, they are also quite correlated in the sense that those that are below the disk are going towards us here on this representation, and those above are going in this way. And if you really look at the full velocity vector of these satellites, and if you look at the angular momentum of this disk structure, basically the orbital poles of the satellite galaxies, the classical satellite galaxies of the Milky Way, are extremely aligned with the normal to the plane of satellites. So you start by fitting a plane to the location of this on the sky, then you take the normal to that plane, and then you compare the normal to that plane to the orbital pole of each of the satellites for which you have radial velocities and proper motions. And so I like this plot because it's really, so that's the number of satellites. So you look at the angle between the orbital pole and the normal to the plane, and I think it's quite impressive, right? You look at the cosine of this angle, and they are all clustered around 1, which basically means that the angle is very close to 0, while you can take different simulations, even those where you do create a plane. Usually you can have a small enhancement here, but not at all at the same level of what is seen there. Now, if you look at lots of simulations, so for instance, in this Sawala et al. Paper in 2023, they say that when they look at both the kinematics and the spatial distribution, that's typically a 1 in 200 case in their simulations. And so that's where we are at. That's where I was saying I don't know what you call an anomaly, right? As long as you don't see that this thing is repeated over and over in other galaxy groups than the local group, then you don't know if it's really a problem. I don't know if 1 in 200 is a problem. I mean, if it's not like this somewhere else, then it just means that the Milky Way is a special galaxy, and the local group is a special group of galaxies, where for some historical reasons this has happened. And maybe it has happened only now also, by the way, that this is a very transient feature. But if this is omnipresent at different scales, and we might know, hopefully in the coming years, then we know if it's a real problem for LambdaCDM or not. At this stage, I don't think we can really conclude. Okay, so dark matter halos. This is something that you, of course, all know too. That a good parameterization of dark matter halos in DMO simulations is the NFW profile that you can basically parameterized by two parameters, which are the concentration and the virial mass defined as M200. And in simulations, you do have a mass concentration relation, which in the end means that with some scatter, it turns out that in DMO simulations, the dark matter halos that you form are basically a one-parameter family driven by mass with some scatter around the concentration, right? So that's interesting in the sense that in principle, you would expect that all galaxies residing in halos of the same mass should have the same gravity. I mean, especially at low masses where galaxies are dominated by dark matter, they should all have the same gravitational field, and so they should all have the same rotation curve. Now, things are a little bit more subtle in the sense that some simulations, not all of them, that have quite aggressive feedback, like the Nihao simulations, they do manage to transform the central custom dark matter distribution into cores. So here you have the central slope of the dark matter halos as a function of m star over m halo within the Nihao simulations. And so here you have basically with some adiabatic compression, you do have something that a central slope which is close to -1 or even a bit cuspier than -1. But in the presence of feedback, you can bring back the galaxies that are here with m star over m halo around few hundred, 1 over a few hundred. You can bring them back to cores. Note that again, because you have a direct relation between m star and m star over m halo, you are still a kind of one parameter family driven by mass, except that you change, you also, in addition to concentration, you also change your slope in these simulations in the central part. But this is still, I mean, you don't have a lot of diversity. Either you do create cores in all these galaxies or you don't, right? But you don't do both at the same time in these simulations. One thing that is interesting, I think, on this plot is also, and that's for sure, there is not a single galaxy simulation set that manages to do that, is that the Milky Way is somewhere here, right, in terms of m star over m halo. And so there is not a single cosmological simulation that can produce a core in the Milky Way. So we don't really know. I think the jury is still out on the shape of the dark matter halo of the Milky Way. But all I want to say is that it's an interesting topic in the sense that if we can prove that the dark matter halo of the Milky Way is quartz, which it might well be, then again, this is really difficult to explain in the LambdaCDM frame. Okay, so I think the fact that in CDM, even when you take into account feedback, you typically still have a one parameter family for your dark matter halos, brings what is one of the most bizarre problems, which is nowadays known as the diversity of rotation curve problem, but which was really well by Swatters and collaborators. And so basically, all in all, what it means is that there is a lot of diversity at a given mass scale in the shape of the rotation curves, in the central shape of rotation curves. And the inner rise of the rotation curve is really following the inner rise of the rotation curve without dark matter, even in galaxies that are fully dominated by dark matter. So this abstract of this 2009 paper was saying that it suggests that the luminous mass dominates the gravitational potential in the central regions, even in low surface brightness dwarf galaxies, which doesn't make any sense because we know that low surface brightness dwarf galaxies are dominated by dark matter. So that doesn't make sense. So this is an example of what I would call the Tully-Fisher twins, in the sense that they do have basically the same baryonic mass, close to the same baryonic mass, the same asymptotic circular velocity, but the shape of the rotation curves are very different and are completely following. So in green, you have the rotation curve that you would have without dark matter. In this color that I don't know the name of, you have the dark matter halo rotation curve and the fit, the total fit in red, right? So these are anasto profiles where you can basically change from cuspy to chord halos. And so you have quite extreme differences in the shape of the dark matter halos of galaxies that have the same maximum velocity or the same asymptotic velocity. So this is summarized on this diversity plot, where you have the maximum velocity Vmax of halos versus the rotational velocity measured at 2 kiloparsec from the center. So that's a direct measure of the gradient of the rotation curve close to the center. And so if you look at here at this scale, you have a lot of dispersion here, much more than what you can get from simulations. And this is directly proportional to the circular velocity due to the baryons alone at 2 kiloparsec. And so this another way to talk about the circular velocity due to the baryons at 2 kiloparsec is to say that it's the surface density of the baryons at 2 kiloparsec. So basically, the diversity of rotation curves is driven by the surface density of the baryons, which doesn't really make sense, or at least we don't understand where this comes from. And all I want to show here is that even if you take the Nihao simulations that are, if you take, so as I was saying, not all simulations do create cores. Let's concentrate on this plot. So here now it's not Vmax, it's Vlast, but the problem is the same. So if you take simulations like Apostoligal or Illustris that don't create, that don't transform the curves into cores, basically you never create all the observed points that are below basically the one-to-one curve here, or close to the one-to-one curve between Vrot and Vlast. Yes, if you look at the Nihao simulations, you do create cores, so you decrease the value of Vrot at 2 kiloparsec, but then you don't have cusp anymore. So basically in this region here, Nihao is just creating cores and it's not producing any galaxy close to the one-to-one line. So basically either too many cusps or too many cores, no simulation produces the full diversity. Okay, so that was the promise of the talk. I still have 15 minutes, approximately. Let's try in 15 minutes to do the whole thing here. I think we can be quite quick, right? So in the sense that warm dark matter, what does it do? To create a core of 1 kiloparsec, you need a thermal relic of about 0.1 keV, which would prevent the formation of dwarf galaxies altogether. So I think if you just rely on warm dark matter to get large cores like the one that you would need in feeble giants that I was talking about, etc., forget about it. This is of course excluded also by the Lyman alpha forest observation. Of course, you can go to warm dark matter that have much higher masses that will bring them close to cold dark matter to a point where you're not going to solve any of the things or you're not going to change any of the phenomenology that I have shown you. So I don't think that that's a way to explain what I just showed you. Can do other things, but not that. Fuzzy dark matter, interesting in its own right. It does create central cores with reduced dynamical friction, which could be useful for the formation of bars. For instance, I was talking about things where you could have subtle differences that could help explain the observations. There are also large-scale fluctuations that are generated by the fact that you have to solve the Newton Schrödinger equations. So this generates large-scale fluctuations in your halo that can constrain basically the halos around ultra-faint spheroidals, and also from streams the stellar streams that can be heated up by these large-scale fluctuations. So these fluctuations are very important for very, very low mass for these axion-like particles. Basically, if you take the constraints from cuspy ultra-faint dwarfs and also from the Lyman alpha forest on how much structure you want to create down to small scales, you end up usually with masses that must be larger than 10 to the minus 20 eV. And among the tensions that I showed you before on galaxy scales, this is not going to, I mean, it's not CDM yet, but it starts to be close enough to CDM to not change much on the problems that I was telling you about. I think the one that has the most chances of completely changing the picture, both for dwarf galaxies, satellite galaxies around the Milky Way, and for the diversity of rotation curves that I was showing you, is self-interacting dark matter. This one very much changes the picture. In that case, the matter power spectrum is not changed a lot, contrary to the other ones where it does change, with self-interacting dark matter, but less. You don't have the sharp cutoff that you get with fuzzy or with one dark matter, and it really changes a lot the dynamics inside Halo. So these are, for instance, simulations where you typically show that the diversity of rotation curves is much more easily reproduced in self-interacting dark matter. Basically, when you have no baryons, you typically do create pores in SIDM, right? And when you have baryons, the reaction of SIDM to the presence of baryons creates even more cuspy halos than you would get with CDM alone. So you get a dark matter halo that is that is naturally forming cores. You don't need feedback at all to form cores in SIDM. And at the same time, which is much more reactive to baryons. So this naturally creates the full diversity of rotation curves. So you can, this is an example where you can analytically try to measure or compute what the shape of an SIDM halo should be when it is around a baryonic galaxy that is here represented by a Hörnquist profile that have different densities for the Hörnquist profile in different masses. And each time you have the equivalent CDM halo in dash, and then the equivalent LambdaCDM halo in dash, and the SIDM halo as a full curve. And so you see that here you have the dark matter only case where you have a large core, while in the CDM case you have the cusp. And then you increase the density of your Hörnquist profile at the center, and then you end up with so this is an adiabatically contracted CDM halo, right? So that's why the profile changes also in CDM, right, in the presence of the galaxy at the center. But you see that in SIDM, you end up with something that is even denser than the CDM halo when your galaxy is denser at the start. So what are the problems of SIDM? Today, it would be nice if SIDM would solve everything, but I don't think it does for a few reasons. Or you have really to vary then the effective cross-section depending on the scale that you are looking at, and that's not always easy to achieve. You can have a velocity-dependent cross-section, but it's really difficult to make it fit all the different scales where you need to solve the problems that I showed you. I would say that in galaxies where there are not many baryons, so typically ultra-faint dwarfs, right, that are completely dominated by dark matter, then the baryons are not sufficient to create cusp. And so the halos are not cuspy enough for all these ultra-faint dwarfs to actually survive within the tidal fluid of the Milky Way. And at the same time, if you take a cross-section that will solve the diversity problem of rotation curves, you typically end up with too dense halos in Milky Way-like galaxies. As I was saying before, it's not clear yet, but certainly you cannot exclude a core in the Milky Way. What is certain is that the Milky Way halo is not super cuspy, but SIDM tends to produce halos that are too cuspy for the Milky Way. So it's not a miracle. You cannot solve everything with SIDM, but it's worth continuing to explore and to see how many other buttons you should turn to maybe pass all the constraints at the same time. What about gravity? How much time do I have for this? 5 minutes? 7. So very quickly, I guess you have all heard about this, but it's still quite impressive, right? That with the very simple idea of Milgrom in 1983, before most of these galaxy rotation curve data were actually measured. So that's what's quite impressive about it. So the idea at the time was just to explain the Tully-Fisher relation and maybe generalize it to something like the baryonic Tully-Fisher relation. He proposed this, and this basically explains all the diversity that I talked to you about. The fact that the shape of rotation curves is directly related to the surface density of the baryons is a direct translation of the fact that MON is basically a modification of gravity that directly depends on the intensity of the gravitational field itself. Which the Newtonian gravitational field is directly related to the surface density in this galaxy, right? M over R squared. So basically, these correlations are fully explained So no problem of diversity or the Tully-Fisher relation is even tight. So here, this is known as the radial acceleration relation. So basically, you have the isolated, the Mond prediction in isolation is basically the red curve here, where you have the observed, the baryonic gravitational acceleration generated by the baryons alone versus the observed one, from galaxy rotation curves up to here and from weak lensing there, where maybe here you have a drop that could also indicate that the external field from large-scale structure is basically killing the Mond effect at large radii. Otherwise, you would end up with infinite energy around each galaxy, which is impossible. So I think all of this is quite impressive. Of course, this simple idea, you have to transform it into a Lagrangian. You can take the Newtonian Lagrangian density in the non-relativistic limits for Newtonian gravity. It looks like this, where basically, I mean, the important thing is that the Newtonian Lagrangian density in the weak field limits as a term which is basically grad phi squared divided by a phi g, right? And that comes from the Einstein-Hilbert action. You can derive this from the Einstein-Hilbert action in GR and go to weak field and get this. And so this is already reminding you maybe what I was telling you on the second slide when I was telling you about KS and scalar fields. That basically this is the kinetic term of the Lagrangian density of the Newtonian potential, right? And so the way basically to get a Mond equation instead of a Newtonian equation, Poisson equation, is to generalize the grad phi square that you have in the Lagrangian density into some function of grad phi square, which when you translate this into terms, so this is for the gravitational potential. If you translate this into scalar field language, it means that you basically are doing KSNs, right? And so then you start from the Lagrangian. This is the Euler-Lagrange equation for fields, and then from the way you play with your Lagrangian, you can compute your new Poisson equation. And so you end up in this case with something that is generalizing instead of having Laplacian of phi equal 4 pi g rho, you end up with divergence of mu of grad phi over a naught being the new fundamental constant of Mond, which is typically 10 to the minus 10 meter per second square. And so you have the generalized nonlinear equation. You can do the same. You can do another one that I don't have time to show here, which is called Q Mond, which is slightly different, but doing exactly the same thing in the end. One of the interesting, so once you have, the general idea of Mond that I showed you, the one that fits rotation curves, and this is not a theory, right? Once you write down a theory that modifies the Poisson equation, then you end up with something that breaks something that is at the core of GR, which is the strong equivalence principle, right? It means that the internal gravitational acceleration in a system is going to depend on the external gravitational acceleration in which the system is falling, right? Because it depends on there is this acceleration constant. So acceleration with respect to what, right? It's the absolute acceleration, including the one of the system that is going to enter the equations. So basically, it's basically leads to so that's what I was saying on the plot of the radial acceleration relation at very small accelerations, that it could fall down because you could go back to a Newtonian behavior with a renormalized value of the gravitational constants when you are dominated by the external field, even though you are well below the acceleration scale of Mond of 10 to the minus 10 meter per second squared. But beyond that, you are also flattening your isopotentials along the external field. And you can also show that you have lopsidedness. And so here, this is the typical boost to the Newtonian gravitational field around a globular cluster that would orbit around the Milky Way. And you can see that close to the center, up to 1 Mond radius. So 1 Mond radius is the radius at which you reach the Mond acceleration scale, 10 to the minus 10 meter per second squared. So that's already a bit far away from the center of the cluster. You have a first barrier here, where basically you have a boost to the gravitational acceleration. So basically, it's more difficult for stars to escape from the center in such a globular cluster. And And at the same time, stars that have arrived in the outskirts, it's easier for them to escape from here than to escape from here. So depending on how the stream of your globular cluster is going to be created, whether it's going to be through disk shocking, then basically stars are going to have it's going to be more difficult for them to go in the leading arm. But if it's a continuous leaking, then it's going to be more difficult for them to go in the trailing arm. And so what someone called Guillaume Thomas showed in 2018 is that when you do simulations of globular clusters in Mount gravity around the Milky Way, you create asymmetric tidal streams. And so the paper was called using stellar streams as gravitational experiments, I think, or something like this, or testing gravity with stellar streams. And so, yes, we were the first to show that this is also a consequence of a model-like gravity. And we suggested that it could explain the asymmetry of the PAL5 stream. And so it's interesting that I mean, I think the jury is still out on the observations on that one. But with Gaia, we have discovered more and more streams of open clusters in the disk of the galaxy. So there's the Hydes stream, the Coma Berenice stream, the NGC 752 stream, and they are all tending to be also a little bit asymmetric and well reproduced by model-like simulations of the creation of the stream due to this asymmetric external field effect. So I think that's a kind of bonus. It's more of a detail compared to the diversity of rotation curves that I was showing you about, but maybe there is something that is interesting here. So let's go back to the very start of the talk. So you might wonder, but you said at the start that you need something like dark matter. So yes, so here I was just showing you what the weak field limit had to be to modify Newtonian dynamics in the weak field limit. But if you want to modify general relativity, then you have to, the usual way to do it is to add new fields on top of the metric. And so this the most recent versions of theories are scalar tensor theories that are called pronon theories, in which basically you have a scalar field, but also it's not simply conformally coupled, and you have the gradient of the scalar field that is entering as a vector field in your theory. So the whole thing is not super elegant as a Lagrangian in the end, but you end up, let's say, with a theory where A mu is going to be basically very similar to it's a projection of the gradient of your scalar field, but you end up with quantities that are Q and Y that are basically the temporal variation of a scalar field and the kinetic term of another scalar field, right? And then the action, the function, the k-essence function, is basically depending both on Q and on Y, and to reproduce mounts. I didn't have time because we were close to the ends, but I didn't have time to show you that the way to modify the Lagrangian density in the weak field limit is to have this f of grad phi square function that with a power 3/2. So that would be the hallmark of a non-Lagrangian. And so you do exactly the same here. You have your grad phi square here, and you put it to the power 3/2. This is going to give you mount, right? At the same time, as I was telling you, if you want your scalar field to gravitate, then the 0 point of the potential has to be non-zero, and that's Q0 here. You have to put a new constant, which is Q0, and that is going to give you something that is not dark matter. That is it's a weird thing that it's something in between dark matter and dark energy. But all in all, it produces a very good CMV power spectrum. So I think the blue one and the LambdaCDM one are completely undistinguishable from each other on this plot. Just showing you that, of course, there are a few functions, there are a few free functions, right, in the theory, but it's completely possible to reproduce the CMB. But at which price? At the price that you are not exactly getting back the Mont-Poisson equation, but you have an additional term here, which is kind of impossible to avoid due to this term it's the mixing term, I think, that is causing it. Anyway, what does it do in terms of the RAR? Instead of having your nice RAR like this, in such theories that are reproducing well the CMB, you tend to have these weird thing in your RAR, these oscillations of the gravitational fields that are related to this nasty term in your. So this is basically a Helmholtz equation that depends on the gravitational potential itself here. This is not very nice. So that's what I wrote here. CMB okay, but at the price of oscillations around galaxies. Or you have to change your parameters as a function of scale again, such that at the scale of the CMB, you don't have the same, the parameter itself is running to avoid things not working. Galaxy clusters, of course. I mean, you probably have all heard that MON doesn't work in galaxy clusters. It's even worse because you have interacting clusters like the bullet cluster, where you basically see that the peak of the gravitational lensing is offset from the main peak of the baryons. It's really complicated to explain if you don't have some additional missing mass in your clusters. One thing that we found recently is that really, if you use a mass follows gas, so if you look at the missing mass in MON in clusters, it's really following almost exactly the profile of the hot gas. You just have to renormalize. So and then you have a cutoff in the outskirts. So maybe this could err in favor of missing baryons, but until we find them, I think then we need to resort on something like the fields of the scalar field theories, the scalar tensor theories that I was showing you before. But they at the same time, I think it's possible to boost the gas profile in the central parts with this kind of theories. Also because it depends on the potential here. So I guess you can do something. But what is going to be really hard is to explain something like the bullet cluster. So that I don't know how you can handle this. Also, if you look at the Milky Way, actually, the rotation curve of the Milky Way agrees quite well with the MOND rotation curve. But if you look at the vertical force, most studies indicate that you do not have as much as a vertical force as predicted by the MOND-like Poisson equations that I was showing you before, because these modified Poisson equations will typically produce a dark disk around the disk of the Milky Way, and this what we call phantom dark matter density in MOND. It's not a real dark matter density. It's the equivalent dark matter density that would produce the gravitational fields. It needs to be rounder. You don't want this dark disk. So again, something that doesn't work so well. Very recent paper that is on the archive since I think 2-3 weeks, where we reprocessed the constraints that you can get on these MOND-like theories from the 13 years of Cassini data, so the orbit of Saturn. Very quickly, so this is the phantom density in the solar system on a log scale. So the sun is here, Jupiter is here, the Earth is here. And so this is basically empty, right? You have no phantom density, no effect of MOND in the central parts of the solar system, and Saturn is somewhere here. But in the outskirts, you have the flattening of the potential and even some negative phantom density, right? But you have some distortion of the phantom density in the very outskirts, right? Past the Oort cloud. But this is going to translate into a quadrupole that is going to propagate inside. And in the end, you end up with a very small anomalous acceleration, which is of the order of 10 to the minus 14 meter per second square, that is predicted by MOND. And that generates deviations of the orbit of Saturn of the order of 100 meters in a few years. But the Cassini data are the meter precision. And so basically the typical prediction of the MOND-like theories is 10 to the minus 26 second to the minus 2 for this Q2 parameter. And the constraints from Cassini are 10 to the minus 27. So again, it means that you need to kill your MOND effect in the solar system. So I think the only way forward that I see in this modified gravity playground is to open the box and look at things that are more general than just, so these are the two Lagrangian density in the Newtonian regime, Aqual and Q-MOND. These are, I think they are ruled out very clearly. We have enough data, especially on small scales, that show that this alone doesn't work. But then you can open the box, as I was saying. And so you could have generalized Q-MOND where you have higher order Lagrangians that depend on the higher derivatives, or you can have more fields. So this is called here tri-MOND, where you have a field phi, Newtonian phi, and then a third field, little phi. And so this, of course, is going to give you more dimension constants, more freedom, and maybe you can pass all the constraints at the same time. Maybe you can say that it's not elegant compared to LambdaCDM. I'm not sure. So I would say that it's one day we haven't taken all that numbers yet. So the game is still open. Thank you.
All right, really quickly, some questions. Yeah.
Thanks for your review. I think you have been fair in putting the problems of the alternative and the. But I would argue also that because in my impression was that when talking about galaxies, you mentioned that the Mond theories or alternative gravity theories were working well. But we have found many galaxies where Mond is also failing, particularly in the last 10 years when we are starting to find galaxies without having too much dark matter, for example, or even galaxies that were so faint that looks irregular, but when you go very deep, you see they are very faint spirals, and therefore the Mond also fails by a factor of 100 or so. So I think that we are also now finding galaxies where Mond is not so nice.
When you are in the regime where we measure good rotation curves, we don't have that. I don't think we have a convincing rotation curve where Mond doesn't work. But what is right is that pressure-supported galaxies, for instance, ultra-faints, they can deviate from Mond quite significantly. Let me go back to maybe the RAR, which is a way to visualize the whole thing all at once. Where is it here? So basically, there are galaxies that are kind of standing here, and instead of going down this way, they basically go to a plateau here, and they are almost always pressure supported, right? So I could have added this to my list of opening the box. That maybe depending on the type of orbits that are supporting the galaxy, the shape of this prediction can change. And so I think ultra faints are typically here, right, in this diagram, and even some classical dwarfs, right, are starting to deviate and are kind of here. So I think you have a point that it's true that by opening the box, it also means that Mond really works well for rotationally supported galaxies in general. And that I don't have a counterexample, but for all pressure-supported galaxies, you are fully right. Okay, you show me, but
Question? Final one.
Hi, thank you for the talk. What do you think are the prospects for measuring you were telling that it will be interesting to measure if the Milky Way has a core or a cusp. Can you maybe comment on what do you think are the prospects for measuring this if you want?
This brings me to my other main line of research, which is modeling the Milky Way with Gaia data plus all proper motion data that we can get in the bulge. Maybe with LSST we are going to get good proper motions for stars in the bulge region. So I think all in all, what you want to do is really model the central regions of the galaxy, or essentially the bar region, and really see. I mean, at some point, even if the dark matter is even with the cuspy halo is completely subdominant there, right? The amount of dark matter that you put as a function of radius in the central parts of your galaxy are going to change the picture at some level of precision, right? So my hope, because we are already, I mean, if you look at the fits that have been made with the made-to-measure models in the central parts, they do favor a core, but the error bars are still a bit large, meaning that something almost cuspy or a shallow, what they call a shallow cusp, is still allowed. I think that if you get more and more precise data here, and if it's really cored, of course, if it's cuspy, then it's going to go back to cuspy. But if it's really cored, I think we are, since the best fit model is already a core, hopefully we are going to move away from I mean, we are going to have the cuspy solution moving away at 2, then 3 sigma. And then it becomes interesting because it really doesn't work. I mean, simulations don't produce such things. So yes, I think these are the prospects. And maybe LSST proper motions. Maybe I'm too optimistic about them, but
Right. Yeah. Final one.
So you mentioned that self-evaporating dark matter has problems, but I didn't get what the problem were. So could you kind of summarize them for us again?
One of the great advantages of SIDM is that it can produce, it can be much more reactive than CDM, and so it can create a much larger diversity, which also depends on the surface density of the baryons, which is exactly the kind, qualitatively, it's exactly what you need, right? So basically, you can have cuspier halos than CDM, and you can have chord halos even without baryons, without feedback, without anything, right? So that's really nice. Two things that are problematic. And I think it's related to the previous question in the context of MOND, but I think it's the same problem in the context of SIDM. You have a few ultra-faint galaxies that are dominated by dark matter and that cannot survive around the Milky Way, in the tidal field of the Milky Way, there's a core. So if you put the SIDM core, let me also give the way out. Most of the galaxies that would host these ultra-faint dwarfs are going to be destroyed. The way forward for this is to say that this is a survival bias, because at some point you can have a gravithermal collapse of the SIDM halos, even without baryons, right? Because it's exactly the same as in a globular cluster. It's a collisional dynamics, right? So the thing is not at equilibrium, and so maybe the ones that we are seeing are the survivors, are the only ones that haven't been destroyed. They are the ones that have gone through the gravithermal collapse. There is a little bit of fine-tuning in this, but this argument is still good. And the other one is the other way around, is that, as I was saying, in the presence of baryons, it really reacts quite strongly to the adiabatic contraction that you already have for CDM halos. In the case of SIDM, you get super cuspy and super dark matter dense halos around galaxies like the Milky Way. And there, as I was saying, the debate is more, is it core or cusp? But not whether the central parts of the Milky Way are dark matter dominated. They are not. And so you have too much dark matter. The reaction of an SIDM halo to the presence of a Milky Way-like disk is that it becomes cuspier than the CDM halo. So that's a bit counterintuitive, but the reaction to baryons is like this. This is what I was showing as an example on this plot, that when the central galaxy is becoming dense enough, then the SIDM halo is denser than the CDM counterpart. Right? Well, when you have no baryons, this is CDM, this is SIDM, this is the same one. Huh? So CDM, SIDM, and then you put the galaxy in the center, the CDM1 contracts, and the SIDM goes from here to all the way here.
That takes the little amount of data which density.
Sorry.
People have gained
but around the Milky Way or Milky Way-like galaxies? Okay. Yeah, okay. But still in the Milky Way, we measure things quite well, right? So you don't want this to happen in the Milky Way. Just the Milky Way alone is sufficient to say you don't want this to happen.
All right. Well, let's thank Benoit for his talk. And he will be visited here for the next 2 days. So if you want to visit to speak with him, well, he will be in my office for the rest.
À peu près fini les tours.